Welcome to the 8th video on classical mechanics and relativity. In this video, we will be discussing about the variation of mass with velocity at relativistic speed. This we will deduce from the laws of conservation of momentum. Laws of conservation of momentum says that when two or more particles collides elastically, the total momentum of the system is constant. This is a universal law. The law should be valid irrespective of the frame of reference or irrespective of the velocity of the moving particle. Momentum of a particle is defined as product of mass and velocity. So momentum P is equal to mass times velocity. Let's consider collision of two objects A and B. A and B are having equal masses and they are moving in opposite direction with equal velocity in the xy plane. When we observe from a frame S which is at rest, the velocity of the particle A is minus Vx in the x direction and the velocity of the particle A in the y direction is minus Vy. The velocity of the particle B in the x direction is Vx and in the y direction is Vy. The two particles A and B collides and moves in opposite direction after the collision. The collision is elastic collision. After the collision, the velocity of the particle A in the x direction is not changed, but in the y direction, the velocity is reversed. Before collision, the velocity of particle A in the y direction was minus Vy. Now, after collision, the velocity of the particle A in the y direction is Vy. So, the velocity of the particle A is reversed in the y direction. After collision, the velocity of the particle B is not changed in the x direction, but in the y direction, the velocity of the particle B is reversed. Initially, it has a velocity Vy, now B has a velocity in the y direction minus Vy. So, in the x direction, there is no change in velocity, but in the y direction, the velocity of the first object and the velocity of the second object are reversed when observed from a frame of reference which is at rest. The change in momentum of the first particle A is equal to delta Pa, which is equal to the final momentum, which is mass times its velocity m0 Vy, minus its initial momentum, which is equal to minus m0 Vy. The minus sign comes because initially the particle A had a velocity minus Vy in the y direction. So we would get delta Pa, the change in momentum of the particle A in the y direction, is equal to 2 times m0 Vy, where m0 is the mass of the object A and Vy is the velocity of the object A in the y direction. Similarly, we can calculate the change in momentum of the second particle B. Delta Pb is equal to final momentum minus initial momentum. Final momentum is equal to m0 times minus Vy. Initial momentum is equal to m0 times Vy. So we would get delta Pb is equal to minus m0 Vy minus m0 Vy, which gives 2 times minus m0 Vy. Now, if we calculate the total change in momentum, which is equal to delta Pa plus delta Pb, which is equal to 2 times m0 Vy minus 2 times m0 Vy, which results 0 change in momentum. So the total change in momentum during this elastic collision is 0 when observed from a frame S which is at rest. So the laws of conservation of momentum is valid here. Now let's consider the same collision from a frame of reference S prime which is moving in the positive x direction with a velocity plus Vx. The frame S prime is moving in the positive x direction with a velocity Vx. Remember, the velocity of the particle B in the x direction is also Vx. From the last class, we know the transformation equation of velocity from one frame to another which is moving with a constant velocity V in the positive x direction, that u prime x is equal to ux minus v divided by 1 minus v ux by c square. Here ux prime is the velocity of the particle in the primed frame of reference which is moving with a velocity v in the positive x direction, and ux is the velocity of a particle in the unprimed frame of reference which is at rest. We can use this transformation equation to transform the velocity of the particle from s to s prime. Here for the particle A, ux is equal to minus vx, since the particle A is traveling in the minus x direction with a velocity vx, and the velocity of the frame s prime is equal to vx. Substitute this, you would get the velocity of the particle A in the primed frame of reference s prime as v prime x of A is equal to minus vx minus vx divided by 1 plus vx square divided by c square, which is equal to minus 2vx divided by 1 plus vx square by c square. This is the velocity of the particle A in the x direction when observed from a frame of reference s prime, which is moving with a velocity v in the positive x direction before collision. After collision also the velocity is same, so the velocity after collision also will have exactly same form. Now let's calculate the velocity of the particle A in the y direction. We know the transformation equation, and if you substitute back into the transformation equation, you would get v prime y of A is equal to minus vy divided by gamma into 1 plus vx square by c square. This is the velocity of the particle A in the y direction before collision. After collision, the velocity of the particle A in the y direction is reversed. So the velocity of the particle A after collision will be having exactly same magnitude but opposite sign. Now let's calculate the velocity of particle B. If you look back to our previous slide, you can see that the particle B before collision is moving in the positive x direction with a velocity vx and in the positive y direction with a velocity vy when observed from the unprimed frame of reference S, which is stationary. So here v will be equal to plus vx and ux is also plus vx. Now if you substitute the value of ux and v in the equation, u prime x is equal to ux minus v divided by 1 minus v into ux by c square, which is the transformation equation. And if you substitute the value of ux and v, you would get vx prime of b is equal to vx minus vx divided by 1 minus vx square divided by c square, which is equal to 0. Without looking into the transformation equation also, you can predict that vx prime should be equal to 0, because the velocity of the particle B in the x direction is vx, and the frame S prime is also moving in the positive x direction with a velocity vx. So both will have exactly same velocity in the positive x direction. So their relative velocity will be 0. So without looking into the transformation equation, you can just simply say that from a frame which is S prime moving in the positive x direction, the velocity of the particle B in the x direction would be equal to 0. So from S prime, the particle B behaves as if it is not moving in the x direction. Now let's calculate the velocity of the particle B in the y direction when observed from S prime. We can use the previous equation, transformation equation, what we used. If we use that, we would get Vy prime of B is equal to Vy divided by gamma into 1 minus V square by C square. This is the velocity of the particle when observed from frame S prime before collision. Now after collision, the particle moves in the opposite direction with same velocity. So the velocity will have a sign change. The magnitude will be same. From the frame S prime also, the particle A have no change in the velocity in x direction, and particle B also have no change in velocity in the x direction. So there is no change in velocity before and after collision for both particles in x direction. The velocity changes only in y direction. Now let's calculate the momentum or the change in momentum of the particle A and B. In x direction there is no change in velocity, so there is no change in momentum. So the change in momentum will be only along y direction. For the particle A, the change in momentum along y direction will be equal to mass times change in velocity. So delta p prime a is equal to m0 times change in velocity is 2 times vy divided by gamma into 1 plus vx square by c square. Similarly, the change in momentum of the particle b in the y direction when observed from a frame s prime, we would get delta p prime b is equal to 2 times m0 minus vy divided by gamma into 1 minus vx square by c square. So if you carefully look into these two equations, you would see that they look similar, except that there's a change in the denominator. In the first place, there's a plus sign, and in the second place, for the particle b, there is a negative sign. So it's very clear that if you add delta p prime a and delta p prime b, you won't get 0, which says that the total change in momentum is not 0. That means the laws of conservation of momentum is not valid here. But the laws of conservation of momentum is a universal law. It should be valid in every frame of reference, irrespective of its velocity. So how can we make sure that the laws of conservation of momentum is not violated here? There's one way, that we assume that the masses are changed during its motion. So the mass of the particle A is m1 and mass of the particle B is m2 when observed from a frame of reference S prime. Now their sum can be equal to 0. So now the delta p prime A plus delta p prime B can be equal to 0. So delta p prime A plus delta p prime B is equal to 2 times m1 vy divided by gamma into 1 plus vx square by c square minus 2 times m2 vy divided by gamma into 1 minus vx square by c square. Now you take one term to the right hand side of the equation, and then you have some common terms like gamma and vy. You cancel out, then you would get and if you rearrange, you would get m1 by m2 is equal to 1 plus vx square by c square divided by 1 minus vx square by c square. So we got the ratio of masses, but we have to simplify it further. For this, we recall the value of Vx prime. So Vx prime of particle A is equal to minus 2 times Vx divided by 1 plus Vx square by c square. Now you square it, you would get Vx prime square is equal to 4 Vx square divided by 1 plus Vx square by c square, the whole square. Now you divide the left hand side and right hand side by c square. Then you subtract it from 1. Then you would get 1 minus v prime x whole square divided by c square is equal to 1 minus 4 vx square by c square divided by 1 plus vx square by c square, the whole square. Now you take common denominator on the right hand side, then you would get 1 plus vx square by c square, the whole square, minus 4 vx square by c square divided by 1 plus vx square by c square, the whole square. Now you expand the numerator, then you subtract the possible terms. Then you would get on the right hand side as 1 minus 2 times vx square by c square plus vx square by c square, the whole square, divided by 1 plus vx square by c square, the whole square. So the numerator is equal to 1 minus vx square by c square, the whole square, divided by 1 plus vx square by c square, the whole square. Now you take the square root on both sides, then you would get the value of 1 minus vx square by c square divided by 1 plus vx square by c square is equal to square root of 1 minus v prime x square divided by c square. Now if you substitute back to the previous equation, m1 by m2 on the left hand side of the slide, you would get m1 by m2 is equal to 1 divided by square root of 1 minus v prime x square divided by c square. Here m1 is the mass of the object A, m2 is the mass of the object B, vx prime is the velocity of the object A in the x direction. And if you rearrange, you would get m1 is equal to m2 divided by square root of 1 minus vx prime square divided by c square. Here m2 is the mass of the particle b, but with respect to the frame s prime, the particle b is rest in the x direction. So there is no velocity for the particle b in the x direction. So you can say the particle is rest in the x direction. So we can call that mass m2 as its rest mass m0. And if v is the velocity of the particle m1, then we can rewrite the equation as m1 is equal to m0 divided by square root of 1 minus v square by c square. So in general, we can write m is equal to m0 divided by square root of 1 minus v square by c square, where m0 is the rest mass, which means the mass of an object when measured from a frame which is rest with respect to the mass, and v is the velocity of the object, and c is the velocity of the light. And m is the mass of the object moving with the velocity v when observed from a frame of reference which is at rest. We can graphically represent the variation of mass with velocity. Here, this graph represents the variation of mass with velocity at relativistic speed. When the speed of the object is very low, the mass of the object is equal to or very close to its rest mass m0. As the velocity increases, you can see that the mass of the object increases, and when the velocity of the object is very close to the velocity of light, the mass of the object will become nearly infinity. Thanks a lot for watching this video. I'm Dr. Pradeep.